In the previous class, we have already discussed about this topic, that is how to load different bands. So this output is already visible in the right hand side that we have covered. But what is our topic of discussion? Now see this highlighted portion. Here what I am doing, see I am working on band 1. So among band 1 to band 6, here I'm working on band 1, and what I'm doing here, I'm just using some project raster function. And here there is a concept of CRS, and also try to remember, whenever I have discussed the previous class, we have discussed about some properties of some specific band and stacking of that. So here we have some concept like CRS, resolutions, dimensions, everything. So today we have to understand one concept, that is why we need band projection. So this is our topic of discussion. So today we will learn what is the meaning of this set of lines and what do you mean by band projection. And here I am working on band 1, but we can work on any other bands too. So now let's start with the concept. So using some specific band is easy, but whenever we need some projection, so the first question must come in your mind, why we are projecting something? What is the need of projection? To understand this concept, we have to understand all these properties in details, right? So let's start the class. Since this concept is very essential, I will start from the very basic concept. That is, I have already discussed that what is this spatial data is all about. So whenever I am talking about spatial data, we can say that these are the data which has coordinates associated with it. Now, what are the concept of coordinates? See, coordinates are locations, or you can say that coordinates are locational address of each and every point on the earth. Whichever point we are defining on the earth, these are known as locational points, right? So, locational points are generally expressed in terms of latitude and longitude. So this is the very basic idea. We know everything about this. But now let's see what are these coordinates. Means each point on earth has given coordinate. And now you have to keep in mind, whenever I am talking about an earth, it has a specific coordinate, that is the earth is a spheroid. So this thing we have to keep in mind, and it always follows a 3D coordinate system. So the most important example of geographic coordinate system is WGS 84. So now our first objective of this class is, what is this WGS 84? So here the answer is, whenever we are talking about Earth and its location, we know that this spheroid always depicts one 3D coordinate system. And this 3D coordinate system is known as geographic coordinate system. And WGS 84 is one of the important example of this geographic coordinate system. So, what is this WGS 84? It is just an Earth centered, or you can say that Earth fixed terrestrial reference system. And it is also known as geodetic data, right? So, it is a constant, and you can say that it depicts some model parameters that basically describes size of an Earth, means Earth size, shape, gravity, and geometric fields. everything is depicted by this WGS 84 concept, right? So this is the basic concept that we have to keep in mind whenever we are learning about geographic coordinate system. Now, in this geographic system, we have some more concepts. So let me draw one diagram, that is, see, whenever we are talking about Earth, so in the Earth we are talking about geographic system. So in this geographic system we have one concept which is known as equator. So basically equator is something which is running horizontally through the middle of the Earth. And we have another concept which is running perpendicular with the equator. And this concept is known as prime meridian. So what is this? So in simple way we can say that whenever we are talking about an equator, and if we have something which is running perpendicular with the equator to the Greenwich term in United Kingdom, it is known as prime meridian. And prime meridian is the origin point of the longitude and latitude. So this thing you have to keep in mind. And it varies from minus 180 degree to plus 180 degree. Now we have some more concept that parallel to the equator we have latitude concept. So what is longitude? So longitude is something that run perpendicular to the equator and vary from this range. And whenever we have the concept of parallel lines with the equator, that is known as latitude, and latitude varies from minus 90 degree to plus 90 degree. So wherever they intercept, means wherever latitude and longitude intercept, that point is known as coordinates, right? And coordinates means I'm talking about address. So the address of the spheroid. So initially I have discussed that whenever we are talking about an earth, it depicts some 3D coordinate, right? And 3D coordinate is something which is known as geographic coordinate system. And any point on earth is basically a particular intersection point between this latitude and longitude. So this thing you have to keep in mind. Now come to the actual discussion. So this part is known to everyone who know basic geography. But see, the whole of the earth's surface is covered with this imaginary latitude and longitude. And what is the utility? It enables us to get every locational points on earth or coordinate. So by using this concept, we can locate everything as a coordinate on the earth. But see, there is one problematic situation. Means, say, whenever I'm talking about a situation that there is two locations, say A and B, right? So it will become problematic when we want to measure the distance between this two location. So what is the problem? So basically it is a very problematic thing if I define that the distance between A and B is 100 degrees, because whenever we are talking about this geographic coordinate system, everything will be represented in degrees whenever we are talking about coordinates and everything. And as a result, whenever I'm talking about two particular location on earth, so distance between these two location can also be depicted in degrees, so it is a problem. So in this case, what we need the term projection. So at this point of time, we need to project the 3D system into 2D space. And this is the point where we need the concept of planar coordinates. So whenever we want to measure some distance on some particular location situated on the earth, at that point of time, the geographic coordinate system or the 3D coordinate system is not useful. So at this point of time, we need a projection from 3D to 2D, and this kind of projection are basically known as planar coordinates, and which are expressed in terms of meters. So this is the first concept that you have to keep in mind. Now, if you want to squash out the 3D space into 2D, then there will be distortion. So this kind of projection is not so easy. Whenever you are performing this kind of projection, you will face some problems. So what are those problems? The problem will be, say, distortion in shape, distortion in size, and also distortion in location. So, in order to minimize those map projection, we are basically going to use the concept of UTM. UTM stands for Universal Transverse Marketer. So, what is the concept of this UTM? So, this UTM is useful whenever we are converting some 3D system to 2D space in order to depict some kind of planar coordinate system. So, by using UTM, we will get the planar coordinates. So up to this is our discussion. And what it allows? It allows us to measure things such as distances, and that is a projected coordinate system, we can say. So geographic coordinate system are expressed in decimal degrees, that is latitude and longitude. On the other hand, the UTM is expressed in meters. So this thing you have to keep in mind. So in order to use that, we have to specify the UTM zone details. So now here you need to understand the basic logic, that is UTM zone. So what do you mean by this concept UTM zone? See, this UTM zone is a 6-degree segment of the earth. And because of this 360-degree circle, we measured 60 UTM zones. So why so? Because 360 divided by 6 degree segments, and we have 360-degree circle, so which is equal to 60. So therefore we are getting 60 UTM zones. So this is the basic concept that you have to always keep in mind. So the marketer uses an upright cylinder of this mapping projection. So this UTM zone is very much essential, you have to keep in mind. And now, along with this concept, we have two or three concepts that we have to remember all the time. That is, say whenever we are talking about some map and we are talking about the raster data, we can say that they are typically images. Means they are image kind of data, we can say this is a raster data. And geographic coordinate systems are always associated with this kind of data. So this comprise of pixels and some regular grid cells. So that can store values, and it can store definitely continuous values. Say I'm giving you one example, say raster of hillshade. So whenever I'm talking about raster of hillshade means it will contain some continuous values of hillshade of a country which is a topographic product. So simple. So raster product means it is just an image. But now let's talk about one more point. So if you are guessing that, okay, I'm talking about raster means now I'm going to discuss about vectors. Now there is one twist you have to keep in mind. See, vectors in spatial data science or spatial data analysis, it is also known as features. So whenever I am talking about vectors, which is also known as features, which presents the world using the concept of some lines, points, and polygons. So whenever we are talking about feature of some image, means basically we are talking about vectors. Now there is one point you have to keep in mind about these vectors. See, since vectors can be represented like the concept of points and polygons, it is good for storing data for discrete boundaries. We know that. So raster is containing information about some continuous data, and vector is something which is containing discrete boundaries, and that can be, say, country border, protected area boundary, something like this. So now the term vector and feature are used quite commonly. So they are used interchangeably with the data format. Now come to the point. So whenever we will use .shp file format, actually we are talking about vector data. So mostly vector data are presented in terms of shape files. But now you have to understand one more point over here. In order to use shapefile, you need to have three different kinds of files in your working folder. That is, whenever you want to access this .shp file, that is the main shape file. So this is the one file that we have to import in the system. This stores basically the geometry of the polygon. You can say that region of interest. So it basically holds the geometry of the polygon. But we cannot use this shape file in isolation. The working folder needs to have another file which is known as .shx file. And in the previous class, we have already discussed about some conversion on this .shx file, which is basically the positional index of each geometry. So what is this .shp file? This shape file contains the geometry of the polygon. Along with this .shp, we need .shx file. And what is this file is all about? This file holds the positional index of each geometry. And again we need another file .dbf file which stores the attribute information. That is, it stores the attributes. So here you have to always keep in mind, whenever you want to access the vectors or the features, you have to access this .shp file. Means if this is the raster and if you are considering some protected boundary on this raster, means you are accessing the vector or the feature. So at this point of time you need to access this .shp file. But this file you cannot use in isolation. At the same time, in the same folder, you should have the positional index file, that is .shx file, and also you have the attributes of this image, that is .dbf file. So this thing you have to always keep in mind. And another kind of feature data is also known as point data. So we have talked about raster, we have talked about polygon, which is also known as vectors and features, and also we can use point data. Point data like something like this on some raster. So when it is useful, so this kind of data are stored in the flat file format. So whenever I am talking about point data, it will be always stored in flat file format. Now you can ask me one question, okay, what is this flat file format? So flat file format means it is a CSV file comma separated value file means you will have one CSV file where you have latitude, longitude and some say species information. So whenever you have this kind of file format, then you will understand, okay, at this point of time you are using point data. Now why it is useful? Say this kind of data are typically recorded in XY format, and it is used to record the location of particular species. So whenever you want to do any research on species related activities, species distribution, species occurrence, at that point of time you need flat file or .csv file. That's why whenever you are accessing point data, it means the source of data will be different. So the common source is known as GBIF. This is one of the common source from where you can acquire this species occurrence related data. So this is all about point data. Now come to the basic topic. What is our discussion? See, I am going to discuss this codes. So in the previous class, whenever we are doing this previous coding, we have already studied that how to read raster data using R. How to modify the CRS of this raster bands, this thing is important because whenever we were loading band 1 to band 6, we know that we have this kinds of properties. And see, this kind of property will include the term project equal to UTM plus zone 48. So this kind of thing, and also we have WGS 84 concept that I was discussing right now. So now to understand this code in details, we have to discuss one or two more points. See here, I have loaded band 1, right? So why I have loaded band 1? Because I want to use it. Now in case of band 1, as you can see, the coordinates are represented in terms of planar coordinate. Now I have already discussed 3D to 2D projection and the concept of planar coordinate, which is represented in meters. So here we have the planar coordinate system. And here it is clearly mentioned that the projection is UTM projection. And what is this zone 48? So while discussing UTM, I have already discussed about the concept of zone. So zone 48 means it is basically falls under Vietnam. So whichever data I have acquired from Landsat, it is from Vietnam. And in this UTM system, everything is in meters. And we can also tell that it's a linear system. Now see here we have the resolution 30 meter by 30 meter. So why so? Because here I have extracted data from Landsat to plot band 1, and Landsat will have the resolution of 30 meter by 30 meter. Now see here what I have done over here. I want to change the CRS. So in that purpose, what I have written, see in R, I have used one function that is project raster, and then I have used some argument. So what is this arguments are all about? Now, if you want to convert or project, see projection is required because 3D to 2D projection is always required. So always we have to do some kind of projection. So if you want to convert or project, say band 1 to a different coordinate system. So in this case, the latitude, longitude, we have to keep in mind and we have to use the concept of long lat. Then we can use at this point of time project raster function of the raster package. So whenever you are using this project raster function, you have to keep in mind that you should have the raster package installed. Then first, as an argument, you have to specify the band that you want to convert. So here I am using band 1, but you can use any band that you want to convert. So now what is the meaning of this second argument? This second argument of this function specifies the coordinate reference system, that is the CRS. that it needs to be changed to. So basically, whatever band I am having now, I am going to convert this band into the coordinate reference system. Then the conversion process is carried out. So this is the way how we can convert each and every band, and here I am using one variable B1LL. So it will take considerable amount of time if I execute this lines of code. However, here you have to keep in mind one point, that is why we have to change the coordinate reference system. And if you understand this concept, then you can easily extract data from any data source and you can change them. Why this coordinate systems needs to be changed, that is, whatever information or whatever band information is there for each and every band, luckily in our case they are on same scale. But in research it may happen that you are acquiring band from different sources and the information that each band is having, they are not same. So at that point of time you have to convert them so that they could be at the same scale and you can use them for further research. See, this is a simple line of code, but this simple line of code will have some information like datum, WGS84, zone information, all this thing you have to know in details. So that's why I am explaining this.